So in this segment, we're going to talk about transistors, and hope you don't mind my joking phrase, transistors for dummies. But the reason I'm calling it that is that most books and even most of the YouTube videos online about transistors goes into the theory of semiconductors and holes and electrons and N channels and P channels and all that. And the reality is you don't need to know that. You need to know how to use them and what makes them work. So I'm going to start with just a little discussion about why is this a big deal? What's the big deal with transistors? And the reality is it was always very, very valuable to be able to control an electric circuit using another electric circuit, right? We've been looking at things like switches, right? You can manually open and close a switch and make something happen with the circuit. But what if you could use an electrical signal to then affect the other electric circuit? And what happens then is that very complex behaviors can be programmed and designed into a circuit. And that's really valuable. In fact, that's the essence, that's the foundation of computers, is that the output of a calculation can affect the next calculation, right? So originally, this was done with relays, and relays are not new devices. They've been around for a very long time. Often we'll call them electromechanical relays because they use an electrical coil to create a magnetic field using a small signal, relatively small amount of voltage and current, to close the contacts of another circuit that could be a very, very large, high power circuit, like it could be used for a home appliance. And in fact, there's relays all over your home, right? A typical thermostat will have 3 relays in it, controlling the air conditioning compressor, the furnace, and the blower motor. A refrigerator has relays in it to turn the compressors on and off, and so on. So this was the backbone of industrial automation for decades before the transistor was invented. And it's got some pros. It's fairly straightforward. It's easy to install and easy to figure out what they are. The problem is they can be a little noisy. They can fail because they're mechanical, right? Things break over time, and they're only good for on-off. It doesn't help you amplify like a small signal, say what you pick up with an antenna from a radio transmission, and turn it into something that can drive a speaker. And for that, we invented vacuum tubes. And this is now we're getting into the 1930s, 20s, 30s, 40s. And that was how radio and television operated for the first half of the 20th century, because they could take small signals and amplify them. They were fairly expensive. You had to manufacture them. They were like complicated light bulbs, and they required very high voltages, a lot of power. They took time to warm up. They had all sorts of problems associated with them. But they did build the original computers on relays and vacuum tubes. But that's why they filled up entire rooms rather than what we now carry around in our pocket. So the transistor was invented by some electrical engineering and physics professors, and I believe it was the University of Illinois, that were messing around with materials, and they found that, hey, we could make this happen. And it totally changed our world. It's hard to look at any aspect of modern life that hasn't been impacted by the invention of the transistor. You can make them so much smaller than, say, a vacuum tube or a relay, and we call them solid state. It means nothing's moving, right? The vacuum tube required high energy and heat to create what's called plasma, which is a different state of matter. And of course, relays had these moving parts. So the solid state there's no moving parts. They'd last in a very long time. They're very, very durable. So transistors come in a lot of shapes and sizes. I'm going to talk briefly in this video about 2: the bipolar junction transistor, the BJT, and the field effect transistor, or the FET. Okay. In the lab, we use a FET because, well, we'll see why they are. They're just so much easier to use. But they're relatively new to the scene. We had bipolar junction transistors for a lot longer. And they are more durable. There's reasons why you may want to use them, but they're a little harder to design for. And I think, hopefully, at the end of this video, you'll see why that is. So the bipolar junction transistor has transistors in general are 3 terminal devices. And in the bipolar junction transistor, the symbol looks like this. And the line without the arrow is called the collector. The one with the arrow is called the emitter, and the one coming into the horizontal line is called the base. Okay, base, collector, emitter, and hooking them up the right way is essential to making them work. We think of the collector, think of it as actually, that's where usually the current, the main current of your circuit flows into it. So think of it as collecting the current. And it flows out the emitter. So the main thing, the thing you're trying to control the current is flowing through the connector to the emitter. Often we have the emitter going to the ground, but think of it as emitting the current. And the base is the controller, right? It's what we do at the base that determines whether or not current flows from the collector to the emitter. Pretty simple, really. So when understanding their operation, and particularly for designing them into a circuit, we can think of the connection between the base and the collector and the base and the emitter as really like two different diodes, somewhat in parallel, right? So the base to emitter junction, that's what we call it, is in fact a silicon diode. And the base to collector junction is a diode. So you can see current's not going to flow from the collector to the base, but it will flow from the base to the emitter, and that's what turns it on. If you get current to flow from the base to the emitter, then it creates a much higher current, or allows, I should say, a much higher current to flow from the collector to the emitter. So your signal, your computer, is what's talking to the base, and your load, your motors, your lights, your sirens, whatever you want to control, they're in a circuit that's being controlled through the collector and the emitter. So since the base emitter junction is a diode, it will only conduct if it's forward biased, right? And for a silicon diode, which these are, that means about 7/10 of a volt. So the base voltage has to be about 7/10 of a volt higher than the emitter voltage, and then current will flow, and then we say the transistor is turned on, right? As long as the voltage of the collector is higher than the voltage of the emitter. Again, think of these diodes as kind of adjusting that. These transistors tend to have these two different kind of modes. We call them saturated and linear. In the linear mode, that collector current will be directly proportional to the base current by some constant beta, and beta is a large number, 10 to 150 to 200 maybe. So 100 is not an unusual value for this for the transistor constant, and that's really useful, as you can imagine, for amplification. So if you're catching this tiny little signal on an antenna from a radio transmission, and we want to amplify it, send it into the base, it creates a larger current. And indeed, one of the first big applications of transistors were radios. In fact, they called them transistor radios, and they were very cool because they could fit in your pocket, whereas the traditional radio was something you had to plug in the wall and warm up for 5 minutes, and it was a tabletop thing, right? So that was when we started seeing, wow, there's something different going on here. So like the LEDs, that base to emitter junction can only handle so much current before it might blow up, right? So you have to allow some current to go through there, but not too much, right? And so almost always for these applications, you want a current limiting resistor. So imagine you want to hook up the Arduino output to the base of the transistor. 5 volts to ground is what is, the diode sitting there. The base to emitter junction is sitting there between 5 volts and ground, but it only has 7/10 of a volt forward bias, so it would fry. So you need a current limiting resistor to just like an LED. And the LED resistor is usually a 220 or 330 ohm. In these cases, you'll see 1K to 10K ohms is a very, very common resistor. Whether or not that's the best choice is something you're going to need to take into consideration if you're designing a circuit around it. You need to supply enough current to accomplish what you want to do, but not so much that it destroys the transistor. Transistor data sheets will tell you what's the maximum IBE, the current from the base to the emitter. But what we want to do, for the vast majority we don't want to kind of turn them partway on or off, right? We're not using them in the amplification mode. That's a pretty tricky design problem. We want to just use them as a switch. And a switch means you throw enough current into the base so that the load, the voltage drop across the load dominates it, and basically there's only a small load, 2/10, 3/10 of a volt drop across the transistor, and it's on, right? So you can, if you throw enough current into that base, it's either on or off. So we're showing this typical application here. I show a base resistor here, that's probably 1K, and some load that will connect to between the collector of the transistor and the supply voltage. VCC, common collector, is what that stands for. So it's where the collectors of your circuit will be connecting. And so as long as that Arduino goes up to 5 volts, it will forward bias the diode. You'll drop 4.3 volts across the base resistor, and current will flow through the base to emitter, and then larger amounts of current will flow from the collector through the load to the emitter. And again, if that doesn't turn on all the way, and you can tell that by looking at your voltage drop from the collector to the emitter, then maybe you need a smaller base resistor to allow more current to go through. So what I'm showing here is that analysis of the base circuit, right? So you got 5 volts in the Arduino, a 1K resistor, and that base to emitter junction, right? And this is what I just kind of narrated through, that you get about 4.3 milliamps. That means you might get as much as 430 milliamps going from the collector to the emitter in the main load. So what we're showing here is what I mentioned earlier, that using the transistor as a switch, if the voltage drop across the load approaches VCC, in other words, if you pump more and more current through it, it generally will have a higher and higher voltage drop, right? There's almost always some resistance in that load. Then that voltage drop across the transistor gets smaller and smaller because most of it's being taken up by the load, and there'll be a limit to that, a limiting value of the V sub CE, the collector to emitter voltage, and it's a 2/10, 3/10 of a volt. And so we talk about that as being saturation, and basically that's the key to using a BJT transistor as a switch. Is just make sure you're supplying enough current through VCC in your load so that the voltage drop across it is almost all of the VCC. So we also talk about it being all the way on, right? That's another way of saying it's saturated. Okay, so that's the BJT. You have to kind of understand that base to emitter junction. You got to worry about how much current's flowing through there. You want to worry that there's not too much current. And I'm setting you up. And there's some BJTs in the kit, right? Some of the smaller ones that look like the thermal sensor we were looking at in the Arduino startup kit. Those are BJTs. Field effect transistors, and there's one that's in a larger package in your kit, does much of the same things, just does it differently. It behaves differently. 3-terminal device. The generic symbol looks like this. There's a lot of different symbols of it. I'm using the simplest one here in this thing. So the terminal that would be the controller, we'll call it, that's the gate. And then we have the drain and we have the source. So GDS, right? Gate, drain, and source are the 3 terminals. And they operate much the same way. The drain is where the collector would be. It's kind of the positive side. It's where the current's kind of entering. The source is the negative. It's where the current leaves. That counterintuitive naming gets to the fact that when the conventions for current were developed, we didn't realize that we had the directions wrong. So what we call current flows in the opposite direction that the electrons actually flow. So mind blown, right? So they named these ends based on where the electrons go, not what we would call current. This is called an NChannelFET. It's very analogous to the BJT I was showing, which is called an NPN BJT. They have other they have families. Both of these have opposing ones called a p-channel FET or a PNP. We won't talk about that right now. Okay, these operate very simple, right? As long as the gate voltage is positive, it turns on, and it doesn't take and how far it turns on is dependent on the gate voltage, not on the current. So whereas the BJT, we call that a current control device, and so you have to kind of modulate the current to work with that. That's not the case with these guys, right? These guys are voltage controlled devices, and so much simpler. When you put a voltage on the gate, it creates an electrical field, and that's what turns it on. So that's the name of this, a field effect transistor. It draws essentially zero current. It may draw a little bit of current at the minute at the nanosecond you apply it, because it's like you're charging a capacitor, but it's a tiny capacitor. And once you do that, it stays on, right, until you can drain that charge away and collapse the field, the electrical field, and then it'll turn off. So if you put a voltage on the gate, and as long as the drain voltage is higher than the source voltage, then current will flow. Okay, much simpler operation. Dealing with voltages rather than current is just a lot easier. If it's not obvious to now, trust me, or you'd figure it out if you were starting to play with BJTs. So much easier to design for a field effect transistor, no doubt about it. Hands down, these are simple. They're more efficient. They don't lose as much. They don't dissipate as much energy while they're conducting, so they're better for high power applications. They are more stable thermally too. They don't tend to, BJTs tend to kind of run away if they get too hot. The cons are they're susceptible to electrostatic discharge. So, the kind of stuff when, like a lot of computer components, because they have these things in them, is if you're in a carpeted room in the wintertime when it's dry, you walk across the room, touch the doorknob, you get zap, right? You get that shock. By the way, that shock is like 10 to 20,000 volts, hardly any current, but it's that voltage that tends to break down the barriers inside these integrated circuits. They're making them a little more robust than they were 10, 20 years ago, so it's less of an issue now, but it's something to keep aware of. Okay, so let's look at a lab where we're taking a field effect transistor and controlling a motor with it. So this is the simple circuit. There's the drain, source, and gate. The gate gets connected to a digital output on the Arduino. Let's say we use a 9-volt battery to run the motor, and there you have it. If you put a voltage on the gate, it allows current to flow. If you take that voltage away, or more precisely set that gate voltage to ground, so you have a place to drain the charge away, it shuts off all of a sudden, very, very quickly. And there was a previous video about inductive loads that talked about that. So that's why we need the flyback diode. So that's it in a nutshell. Using transistors on and off. You don't have to know about electron holes. You don't have to know the theory of semiconductor material. 3 terminals. How do you hook them up? Okay, that's it. Thank you.